Hello, everyone, and welcome to Novel for GCSE. So, in this live stream, we're going to just be continuing off of the physics that we did yesterday. So, yesterday we covered forces and we began to do a little bit on waves. So, now I'm going to just go straight into the harder topics of waves. So, we're going to go into radio waves, electromagnetic waves. Hopefully, I'll be a little bit quicker in this live stream so we can get more done. If you have any questions, just feel free to ask or comment them as well if you're watching this not live. Okay, so we're going to go over radio waves first. So, radio waves are a type of electromagnetic wave. So, when we're talking about electromagnetic waves, EM waves, electromagnetic waves are made via oscillating currents of electric and magnetic fields. Like that. So what happens is we have something called alternating current. And when we have alternating current, this is made up of oscillating electrons. The electrons are moving, that's what creates that charge. Now, as these charges move or oscillate, that means that they produce an oscillating electric field and an oscillating magnetic field. And that's what we refer to it as the electromagnetic part of the wave. It's all right, Sophia. Thank you for your comments. I'm glad that they've been helpful for you guys. Okay. So, with this alternating current, as the charges are oscillating, they're producing that oscillating electric field and that oscillating magnetic field, and that creates electromagnetic waves. So, we also need to know about the frequency of the waves. So, the frequency of the waves produced will always equal the frequency of the alternating current. So, we've just looked at how electromagnetic waves are linked to alternating current waves. So to alternating current and electromagnetic fields, they have the same frequency. Now, frequency just means the number of waves that pass a point per second, and it's measured in hertz. So both alternating current and electromagnetic waves have the same frequency. Thank you guys for your comments. Okay. Now you can produce radio waves, as we said, using an alternating current in an electric circuit. So what you will need to do, so in order to produce radio waves, which is just a specific type of wave, what you're going to need is firstly what we call a transmitter. And then you're also going to have on the other side a receiver. Okay. So the transmitter, the purpose of the transmitter is to have these alternating currents. So this alternating current sorry, I'm just checking if the live stream is working. Okay, sorry. Yep, just double checking. So, as we said, radio waves, you need a transmitter and you need a receiver. So, what happens is when you are transmitting the wave from the first thing here, the transmitter, what happens is you are getting electrons. So imagine the transmitter contains these things called electrons, which we know produce a charge. So what happens is these electrons in the transmitter start to oscillate, start to move around, which means their charge starts to move around. Okay, and what happens is because this charge starts to move around, this generates radio waves. So as the electrons move, this creates radio waves. Now what happens is with these radio waves, it then oscillates and emits these radio waves towards the receiver. Now, these emitted radio waves transfer energy. So you've got the transmitter contains these electrons that are oscillating, and because they're oscillating, they're producing loads of different charges, and that creates radio waves, and this transmitter then emits the radio waves to the receiver, and the receiver then absorbs these electromagnetic waves, these radio waves, and then it causes the electrons in the receiver to oscillate as well. So then you're going to see the receiver electrons start to oscillate. And that's pretty much how the radio waves work. So the receiver has this, and then what happens is if you were to connect up a alternating current, then the alternating current could be produced via this system. Now, the whole purpose of this system, so when the energy is transferred via waves, is so that you can create a complete electrical circuit, and this complete electrical circuit that generates alternating current. So radio waves are important because they allow you to generate this alternating current that can be used for things like TV signals. So what are radio waves mainly used for? So there are different types of radio waves, firstly. So we've discussed that radio waves are a type of electromagnetic radiation made from electric and magnetic fields. Now, radio waves normally have a wavelength of longer than 10 centimeters. Now, they're classified into different types of radio waves. So there's long wave radio, and then there's short wave radio. So long wave radio tends to have a wavelength of 1 to 10 kilometers, whereas shortwave radio only tends to have a wavelength of between 10 to 100 meters. Now, when we're talking about long wave radio length, this means that if you were to transmit a signal from London, you could receive this signal from halfway across the world. And the reason why is not only because we call it long wave because of its long wavelength, but also because the long wave radio does something called diffracting, and that just means bending. So the long wave radio diffracts or bends at the curvature of the Earth. Which just means that, say if you were on Earth and say this is London at this point here, and you were trying to get it to this place A. Now, what that means is that these waves, because normal waves just travel in a straight line, but these waves, because they diffract at the curvature of the Earth, they are able to move alongside the curvature of the Earth. So even if the transmitter, which will be found in London, and the receiver, which will be found in zone A, so even if they are not even in the in the line of sight, they can still transfer this long wave radio. Now, this is different for short wave radio signals. So these are similar to long wave, and they can be received long distances from the transmitter, but they work differently. So with short wave radio length, they are actually reflected by the ionosphere. The ionosphere is this layer of charged particles around the Earth. And because of this layer of charged particles around the Earth, as it moves in a straight line, it then is reflected back to Earth and it moves in sort of a zigzag shape. And that's how shortwave radio length works. So it can still travel long distances, but just uses the ionosphere, whereas long-wave radio length uses the curvature of the Earth to diffract. Now, when we're looking at something like Bluetooth, Bluetooth is an example of a short-wave radio. So when we're talking about Bluetooth, you can use short-wave radios to send data over short distances from the transmitter, because what happens is they're reflected from the ionosphere, which is that electrically charged layer. And as they're reflected, this allows you to send electrical signals along short distances without wires. So wireless connections tend to be shortwave radio. Now, you also have medium wave signals as well. They don't tend to ask you about this, but this reflects from the ionosphere as well. Now, when we're talking about the radio waves that work for TVs and terrestrial, what happens is they have very short wavelengths. So TVs and FM radios, all of these things have very short wavelengths. So in order to get the reception, you need to be in direct sight of the transmitter. Okay. Sorry about that. I think there's just some issues. So yeah, with the TV, there's a very short wavelength, and that means that if you wanted to experience the electric current, the signal from there, you would need to have the transmitter be in direct sight of the receiver. So the receiver and the transmitter needs to be in plain sight with each other. So your TV would act as the receiver, and the transmitter would be the signal box normally, and they would have to be close together. If you didn't have the signal box, then the TV, because it's a short wavelength, it means that you wouldn't be able to reach it. Okay, now moving on to different uses of more simpler waves. So that was the hardest part of this topic. Now moving on to uses for things like microwaves, microwave ovens, infrared. I know that part was definitely a difficult part of the topic, so hopefully you understood that. But let's move on to other electromagnetic waves. So, microwaves. Microwaves are actually used by satellites, so that's a key usage for satellites. Now, the reason why microwaves are used for satellites is, and the communication of satellites, including TV signals and satellite phones, is because in order for it to be a good wave, it needs to pass easily through the Earth's atmosphere, which is really watery. And for satellite TV, the signal from a transmitter is transmitted into space. So, microwaves, when you have these satellites in space, imagine, and in order to be a good microwave for transferring TV signals, it would have to be able to leave the atmosphere of the Earth, which is really watery, and get to that satellite. And it will then be picked up by that satellite receiver, so that the satellite will act as the receiver in that situation. And once it's picked up it then orbits thousands of kilometers above the Earth, and it then transmits another signal back to the Earth in a different direction. So it acts as the receiver and the transmitter, and that's why it's used for communication with satellites. So that's how microwaves work. So it's used for communication to and from satellites. So you have your TV. Initially, your TV acts as a transmitter, for example, sending signals using microwaves to the satellite, and the satellite acts as a receiver. And then the satellite sends things back to Earth, acting as a transmitter, and it's normally to a different part of the Earth. Now, microwave ovens use another wavelength of microwaves. So, one wavelength of microwaves is used for satellites. Now, another wavelength is used for microwave ovens. So, a key fact that you need to know about electromagnetic waves is that electromagnetic waves always transfer energy from the source to the absorber. And this is exactly what goes on when we're talking about microwave ovens. So it's going from the source, which is normally the heating element, which emits these microwaves, to the food. So the heat element to the food. Now, as we said, in communications, the microwave needs to pass through the Earth's watery atmosphere. In microwave ovens, the microwaves need to be absorbed by specifically the water molecules in the food. So when you think of microwave, you should always associate it with water molecules, because we looked at how microwaves in the satellite, they need to be able to penetrate through the Earth's watery atmosphere. And when we're talking about microwave ovens, the waves need to transmit to the food's water molecules and heat those up in order to heat the food up. So they obviously would have to use a different wavelength. So ensure that if you're ever having to differentiate between the two uses of microwaves, say that it is a different wavelength. Because obviously this one needs to be absorbed by the water and this one needs to go through the water. So the water molecules then transfer the energy of the heat to the rest of the molecules by heating, and that quickly cooks the food and heats it up. So that's enough about microwave. Let's talk about infrared. So, infrared. Infrared radiation is given out by all hot objects. And the hotter the object, the more the infrared radiation is given out. So right now, you obviously have a specific body temperature that's probably hotter than the rest of the room because you're a living organism. So because you're warmer than the rest of the room, you are giving out infrared radiation. You're giving out heat. Now, infrared cameras use infrared radiation. And what they do is they detect the infrared radiation and monitor the temperature. So the camera detects the infrared radiation, turns it into an electrical signal, and then displays it on a screen as a picture. So the hotter the object is, so if there was a really hot object, then what would this do? This would cause the cameras to detect this, and then it then turns this into a signal that can be found on a screen. Now, as we said, the hotter an object is, the brighter the signal appears. For example, energy transfer from a house's thermal energy store can be detected using infrared cameras, and it will tend to be warmer where there's people. So imagine it would produce images like this, infrared cameras, and say if there was a person sitting here and there was a person sitting here, then in those areas that would be where most of the infrared cameras would detect a lot of the radiation that's coming from this. And the hotter they are, then the brighter they are. So they're more likely to be brighter and darker colours if they're releasing more radiation. Now, absorbing infrared radiation causes objects to get hotter as well. So food, as we said, can be cooked using microwaves, but food can also be cooked using infrared radiation. And the temperature of the food increases when it's absorbing this infrared radiation, for example, from a toaster's heating element. So toasters are an example of something that uses infrared radiation. And what actually occurs in toaster is that the temperature of the bread increases, and the temperature of the bread increases because it's absorbing the infrared radiation that the toaster element is emitting onto it. So the bread absorbs infrared, and then this causes the temperature to increase and it to heat and cook. Now, electric heaters work in the very similar way. So electric heaters contain a really long piece of wire. And this wire heats up. And this heats up when a current flows through it. So you've got a current flowing through it, and that's why it's called the electric, and then the heater as a part of the fact that because the wire gets so hot, it starts emitting loads of radiation and infrared radiation, and this then causes the room and the atmosphere to get hotter. Now, if you ever wondered why sometimes if you heat a wire up, it starts to glow, then what that means is that you've heated it up. So not all of the radiation is actually infrared. Some of the radiation is actually visible light. So when you ever see something start to become lighter and glow really brightly because you're heating it, it's not just infrared radiation of the heat, but it's also visible light radiation as well. Now, the emitted infrared radiation is absorbed by objects and air in the room, and energy is transferred from the infrared radiation waves to the thermal energy stores of objects. So the infrared waves then transmit this heat, and the energy is then transferred into making you feel much more warmer. So those are microwaves and infrared radiation waves. Let's talk about more about visible light, because we mentioned visible light. So when we're talking about visible light, a key thing is here that fiber optic cables use visible light to transmit data. So you may have heard of fiber optic cables if you ever see an advert for things like Sky. And the reason why they're advertising fiber optic cables is because it's basically the energy, instead of being just a normal wire of metal and the electrons are transferred along the metal, instead it's a glass tube. And what happens is, because it's a glass tube, it causes the light rays to bounce as they are being transferred. So the light rays bounce back and forth along the fiber. So you've got the green thing, which is the glass fiber, and you've got the red line here, which is the light bouncing and visible light. So the optic fibers are these thin glass or plastic fibers, and these are carrying the data from the telephones or the computers over long distances as pulses of light. So the whole purpose of this is to carry data over long pulses of light. Now, the reason why this works is because of the reflection. So the light rays are being bounced back and forth until they reach the end of the fiber. So visible light is used in optical fibers. Light isn't easily absorbed or scattered as it travels along the fiber. So that's why visible light's being used. So if you ever wondered why aren't there any other electromagnetic radiation being used in fiber optic cables, because visible light, it's really hard to absorb visible light, as you can imagine, and it's really hard, it's also difficult to scatter them in this case. So what happens is the only choice for the light is to just be transferred. So there's much less energy wasted as well. So that's fiber optic cables. Now let's talk about ultraviolet, UV. So UV radiation is the thing that gives you a suntan. So fluorescence is a property of certain chemicals, whether UV radiation is absorbed and then visible light is emitted. So when we're talking about if an object is fluorescent, then it normally is a combination of both UV light and normal visible light. So ultraviolet is absorbed, and this then causes visible light to be emitted. So that's when we have the property of fluorescence. So if you're ever asked in an exam situation, how does the property of fluorescence come to be? You can talk about how it contains chemicals that the ultraviolet light is then absorbed and the visible light is then emitted. And that's why they look so bright, because the ultraviolet fluorescent things actually are emitting light. Now, fluorescent lights actually generate UV radiation. So if we're talking about fluorescent lights, these actually generate UV radiation as opposed to absorbing it. And as it generates this UV radiation, it is then absorbed and re-emitted as visible light by a layer of a compound called phosphor on the inside of the bulb. So if we're talking about UV lights, just to give you an introduction as to how that works. So imagine this is a bulb, and what you have here is you have the chemicals that are giving out the UV radiation, so the certain atoms. And as the UV radiation is given out, what we have on the sidelines is this compound called phosphor. And what this phosphor does is this phosphor re-emits this, so absorbs the ultraviolet and re-emits it as visible light. So absorbs the UV rays that's being made in the bulb and re-emits these as visible light. So the same thing as we just discussed with anything that's fluorescent. So it's taking the idea of, in order for something UV to re-emit it as visible light. And UV bulbs do the exact same thing. So UV radiation is made, the phosphor then absorbs the UV radiation and re-emits it as light. And that is how that's supposed to work. Now, UV radiation is also produced by the sun, and exposure to UV radiation can give people a suntan. When it's not sunny, some people go to tanning salons where you have UV lamps, and they're used to give you an artificial suntan. However, if you had overexposure to UV radiation, it can be really bad for you. And you might be saying, okay, well, if that's really bad for you, what about the fluorescent lights? Because they are producing UV radiation. Well, the reason why they're not bad for us is because they only produce a really, really small amount of this UV radiation. So it's not dangerous at all. Okay. And you may also see UV radiation in security pens, which could be used to mark property with your name. So under the UV light, the ink will glow, but it's invisible otherwise. So what we're saying here is that, say if you've ever bought one of those pens, that is a glow in the dark pens. They only show up once you start shining UV light on them. What happens is it contains this special sort of magic ink, and what happens is once you shine a UV light on it, then it will only start to glow. And the reason why it starts to glow is because it absorbs the UV radiation, and then it starts emitting this UV radiation as visible light. And as it emits it at visible light, it then becomes visible, and that's why you can see it. But when you take the UV away, it can no longer absorb UV, so it no longer emits the visible light. So it's more fluorescent than the ink being special. Now, when it's not sunny, some people, we've gone through the tanning salons as well. Okay, so let's talk about X-rays and gamma rays, and then that's the final bit of the uses of electromagnetic radiation. X-rays and gamma rays. So radiographers and in hospitals can take X-ray photographs of people if they have things like broken bones. So what happens is when you're looking at the human body, if you were to shine X-rays on this body, what would happen is they would actually easily pass through the human flesh. But they wouldn't easily pass through things like bones and metal. So what happens is it just creates an image where it just leaves gaps in the bones because where the bones are supposed to be. And as they leave these gaps, you can then notice where the bones are. So that's how you can see how an X-ray image produces an image of just the skeletal system or the skeletal system. Because what happens is X-ray could pass through soft tissue like skin, but it just stops and reflects at the boundaries of the bones. And that's how you can get an image of the skeletal system. Now, radiographers use X-rays, but also they use gamma rays as well to treat people with cancer. So, although X-rays can be used just to get an image, X-rays can also be used to treat cancer, and that's called radiotherapy. Now, in radiotherapy, what happens is because there's so much X-ray and gamma ray being targeting your people with cancer, the high doses end up killing all living cells, or they could kill all living cells. So what happens is the doctors direct the really powerful amounts of X-ray and gamma ray just to the cancerous cells. Just to the cancerous cells, and then they don't direct it to the healthy cells because they don't want the healthy cells to be destroyed. So that's how radiotherapy works. It's a combination of using X-rays and gamma rays, which are really concentrated, and they are actually really dangerous because they could kill all living cells. So the doctors are really specialized in what they're doing, and the radiographers in those hospitals direct it towards cancer. Now let's just talk a bit about gamma radiation. So gamma radiation is what can be used in something called a medical tracer. So you may have looked at medical tracers when I did my live stream on paper 1, radiation. But just in a little bit more detail, the purpose of medical tracer is where you're using gamma emitting sources to inject inside the patient, and then over time, because it breaks down, it just follows the progress into the body and highlights and reflects at the boundaries. Now, gamma rays are really well suited because it can pass out of the body and through the body, and whilst it's passing through the body, it can also be detected. So gamma rays are more specifically used if you want to just view one part of your body and look at a specific part. For example, if you have had heart attack problems, then you will be using gamma rays to just go to your heart and produce a more detailed image, and an X-ray is used for your whole bones and skeletal system. And both of these can be really harmful to people. So radiographers take special steps in order to prevent them from all their cells from being killed. For example, things like lead aprons, lead screens, leaving the room, keep their exposure down to a minimum. And moving on to the dangers of electromagnetic waves, before we would have finished the electromagnetic topic. So, let's talk about the dangers. So, some EM radiation can actually be harmful to people. When EM radiation enters your living tissue, it's often harmless, but sometimes it can create some issues. Now, the effects of each type of radiation are actually based on how much energy the wave transfers. So, the danger of each electromagnetic wave is dependent on the energy that it transfers. So, if we were to go back to our knowledge on the electromagnetic spectrum, we have radio waves, microwaves, infrared radiation, visible light, UV radiation, X-ray radiation, and gamma ray. So what's happening here, so as you go across and across, what's happening is the wavelength actually decreases. So it looks really slow from the beginning, and then it just gets really quick and really quick and quick and quick and quick. So what happens is the wavelength decreases as you increase the frequency. And what we're trying to say here in terms of the danger is that as you're increasing the frequency and decreasing the wavelength, so as you're going across from radio waves to gamma waves, it produces more and more energy, and therefore it's more and more dangerous. So when we have low frequency waves, such as radio waves and microwaves, these tend to not be too bad for you. And what they do is they don't really transfer much energy, and they just pass through your tissue without being absorbed. So with these low frequency ones, there's not much absorption at all. Then moving on to the higher frequency waves, such as UV, X-ray, and gamma. UV, X-ray, and gamma can actually be quite bad because they transfer a lot of energy because of the high frequency. So as they transfer a lot of energy, they can actually cause a lot of damage. Wavefront diagrams. Let me see. Oh, what do you mean, the lenses and the concave and the convex lenses? Because we can go through those, if that's what you mean. But yeah, we're almost on there. We're just talking about the dangers. So the lower frequency is not really bad for us because they don't really are absorbed into soft tissue. But the higher frequency have higher energy and therefore have the ability to be really damageable and destructive to us. Now, when we're talking about UV radiation specifically, UV radiation damages the surface cells. So when we're saying that UV radiation can be used for getting suntans, they're also really bad because they can damage the surface cells, such as causing skin cancer and damaging the skin cells, because too much exposure and prolonged exposure to UV radiation can cause cancer. And also, UV radiation causes people to age prematurely as well. So if you've ever seen people who get loads of fake tans from UV radiation, their skin seems quite old and begins to become premature. Okay. Um, Let me just check the wavefront diagrams that you're mentioning for refraction. There's not there's the ray diagrams. I don't know if the ray diagrams are what you mean. But yeah, I'm just going through the textbook and I'm not able to find them. Yeah, I think there's ray diagrams, but I've never heard of wavefront diagrams too much. I might make a short about them later, if that helps you. Okay. So let's just continue because I'm not too familiar with the wavefront diagram, so I won't be able to probably cover it in this stream, but I'll try and do a short about it if that helps you. Oh wait, I think I know what you're talking about now. 1 second. Okay, let me quickly go over them. Let me go over the wavefront diagrams. Okay, so as you know, when a wave crosses any boundary between materials, it always changes direction, and that's called refraction. So, for example, if you had incoming light, and it met a boundary, then what would happen is, obviously, if this material was transparent, and let's assume the material is transparent, then what would happen is the angle at which it comes at, and then if we were to draw a normal, which is this imaginary perpendicular line, because it's traveling from the air into, let's say this is a glass material, so it's going from a less dense area to a more dense area, it moves towards the normal. Okay, and that's called refraction. So all you need to understand about that is that when you're talking about waves moving through a material, it will always change angle and it's refracted. Now, as we said, how much it's refracted depends on the wave speed, and the wave speed depends on the density. And as we said, because glass is a solid, it's more dense than air, and that's why it slows down. Now, you were talking about the wave front diagrams, so let's look at them. So when we're talking about wave front diagrams, the wave fronts being close together show how a change in. Yeah, I know that's a ray diagram. I'm just showing you. Okay, so the wave fronts being closer together shows a change in the wavelength. So if it's going from a less dense area, as we said, so we're going to use the same example that I was showing here. So a less dense area, then the waves will be distanced. But then if it's meeting this boundary, so imagine the boundary of the material is here, then it becomes more dense. So let's say this part of the ray diagram is the air, and this part of the diagram is the glass. What's happening here is you have the waves on the left-hand side, and as they are moving, they're quite distant because they're in the air. And the wave fronts then become much more closer together in the denser material, so in the glass. And this shows that there's a change in the wavelength. So the whole point of these wavefront diagrams is to show that there's also a change in velocity. The whole point of these wavefront diagrams are to show how waves begin to slow down if it's going in a denser material, and as they slow down, two things happen. The wavelength changes and the velocity changes. Now, if you were to notice, okay. And if you were to look at another method, so if you were to look at, say, if it was going into from a denser area to a less dense area, so say if it was going from glass to air, then it's moving from the denser region to the less dense region. And what's happening is that because it is denser, it's going to be more close together here. And that's the reason why it's more dense is because the reason why it's the wave speed is slower here is because it's more dense. So I know in your comment you were saying that you don't refer to density. Well, you can actually refer to density because the density is the reason why the waves actually slow down. And then in air, they're more spread apart, and that's because in air they are able to move more, and then because of the lower density, this means that the wave speed is higher. Yeah, that's correct, Maddie. Okay. Now, you also have wavefront diagrams of when it hits at an angle. So imagine it was to hit at an angle like that. So that means that the perpendicular normal would be this direction for this side, and then if it was to hit at an angle, say it was that direction or that side. So what you get is you get the normal, let's say the left-hand side was less dense, and the right-hand side was the more dense. So remember, in the less dense, they're spaced out. And then once they hit this boundary, because it's hitting at a different angle, the wave then changes in direction and starts moving in that direction. And let's say because it's more dense, it's more closer together. But overall, you're not going to be too much asked about wavefront diagrams. The most they'll do is show one to you. I don't think they'll necessarily ask you to draw one. But just remember, if it's denser, then the lines will be closer together. If it's less dense, then the particles will be further apart. I hope that answers your questions. But yeah. Okay, let's go back to the damage and dangers of electromagnetic waves. So This is for AQA. Don't think you're failing. You've still got time to learn this. You can do this. You definitely have a couple of hours, and then you can do your absolute best. And then at least a lot of you guys will be done by this Friday, or some of you will still have exams the following week. I think further maths, some people were saying, weren't they? But or engineering, DT, all of those subjects you guys have. Okay. So we've talked about the dangers of UV radiation, X-rays, gamma rays. So, no, sorry, we haven't talked about X-rays, gamma rays. We said that UV causes age premature and skin cancer. So when we're talking about X-rays and gamma rays danger, these two have danger because they are types of ionizing radiation. So all of these radiation have their subcategories. The UV radiation is damaging surface cells. X-rays and gamma rays damage and target electrons. So they throw electrons at your cells, and then this causes your normal body cells to start, undergoing mitosis a lot quicker. And then this causes, because it happens so much, it causes cancer to form, or cancers or tumors. I'll try past papers. Wish me luck. I'm Edexcel, so I'm just going to revise by textbook and maybe Edexcel video. Thanks. Good luck to you. Okay. Great. So we can talk about that. So those are the damages. We've got radio waves and microwaves. They don't have many issues. They're just absorbed easily. UV radiation, it causes skin cancer. It's absorbed by the surface cells, causes age prematuring. X-rays and gamma rays, types of ionizing radiations, can knock electrons off healthy cells, which could cause cancer, cell destruction, gene mutation, any of those things. Now, in order to measure the dosage of the risk, we use something called sieverts. So that's the way we measure the risk of a radiation dose. So whilst UV radiation, X-rays and gamma rays, whilst all of these can be quite harmful, they're also really useful. So before any of these types of electromagnetic radiation were used, people would look at how the benefits outweigh the health risks. For example, for those people who have cancer, although the risks of undergoing radiotherapy are quite bad, because obviously it's not healthy for your normal cells, it can kill living cells, both the X-ray and the gamma ray. Although they're quite bad, some patients will choose to have the pain of the radiotherapy above having the possibility of them dying from cancer. So that's why you have to measure up and balance the risks and does it outweigh the health risks in total? So, for example, the risk of a person getting involved in a car accident, developing cancer from having an X-ray photograph taken, is much smaller than the potential risk of not finding and treating their injuries. Okay, so radiation dose measured in sieverts, as we said, it's a measure of the risk of harm from the body being exposed to radiation. So when we're looking at radiation dose, that's a measure specific to humans. So radiation dose is how much the body can take. And that is a measure of risk of harm for the human body being exposed to radiation. So pretty much how much radiation can the human body be exposed for, and how much harm will that inflict. This is AQA. I did actually go over forces in the previous live stream, so if you wanted to look over that in the previous 2 physics live streams. But thank you for your question. Okay, so although radiation dose is not a measure of the total amount of radiation that has been absorbed, it's more of a measure of the risk. So it's more of a measure of the risk of the harm from the body. Now, the risk doesn't depend on the total amount of radiation absorbed and how harmful the type of radiation is. So, radiation dose measures the risk of harm from the body by absorbing radiation, and it's dependent on 2 sub things. So the first is the amount of radiation, and the second is how harmful the radiation is. So the harmfulness of the radiation. So if there was a lot of radiation, that would cause the radiation dose to increase, because that's a risk of harm increasing. And if the radiation dose was quite harmful, then that also causes that to increase as well. Now, risks can also be different for different parts of the body. So a CT scan uses X-rays in a computer to build up a picture of the inside of the patient's body, and it shows how you're four times more likely to suffer damage to your genes and added risk of harm if they had on your chest, if they had put radiation in your chest, as opposed to if you had radiation in your head. Okay. Let's now move on to lenses. So, firstly, what is the purpose of a lens and why do we need lenses? What are they used for? There are loads of different questions that you could be asked. So, lenses, the whole purpose of lenses is to help people see. And what they do is they refract light, which just means because the light is moving past two different materials, so from the air to the glasses part of it, it's causing the angle to change and causing the direction to change, and therefore we call it refracting, so it bends the light so that you can see it and causes it to change direction. Now, there are two main types of lenses. There's convex lens and there's concave. Now, concave lenses form this shape and convex lenses form this shape. So in terms of diagrammatically, a convex lens tends to be represented with... So a concave lens, is represented with lens like this. And a convex is represented just by an arrow like this. Convex and concave. Now, the purpose of them is that convex lenses bulge outwards, and the whole purpose is to cause rays of light to parallel the axis and be brought together, converge. So let's just look at a diagram that might make that simpler for us to understand. A convex lens forms the shape like that. And with this convex lenses, it bulges outwards and causes rays of light to parallel the axis. So what it means by the axis is this straight imaginary line going through the ray, and that's called the axis. And what it does is it gets these light rays to move and be brought together towards the axis. So you have the light rays, which are coming from all directions. And then what happens is, because of the lens, it then causes it to bulge together towards a point on the axis. Like that. So the outward structure, the curved outward structure, helps the rays of light parallel the axis and be brought together. So this is called, they converge. The rays of light converge together. And sometimes the point at which they all meet here on the axis is referred to as the principal focus. So this is where you're allowed to see. Ideally, if you're looking at in terms of the eye, it would be on your retina. Now, concave lenses bend inwards. So if we were to talk about concave lenses, concave have got that inward bending shape. And what that does is, imagine we have our axis in the middle, And then you have all of your rays coming at normal angles. And with concave lenses, it causes the parallel rays of light to actually spread out and diverge. So instead, it'll go like that and go away from the axis. Now, let's say if there was one that's going along the axis like that as well. Now, what this does is because they're all going out at different angles, you can actually connect the ends of them to a focus on this point. And you can see that, maybe I should make that bigger. So you can, if you were to connect each of the ends of the lines like that, then you could see that there's actually a point here, just like the principal focus on this side. So here, this is the principal focus. So we've got the concave lens, which causes the parallel rays of light to converge alongside the axis on the principal focus, and then you've got the concave lenses, which is because of the inwards, it causes the parallel lights to actually move outwards and diverge. So we called the first one converge, and this is called diverging. They're spreading out. And as they diverge, the point at which they all meet in front of the lens is called the principal focus. Now, these black lines here, they actually don't exist because remember, we just connected them up and said that they all would meet. So these black lines are called virtual rays because they are not real. They're just virtually there, but they're not real. Whereas you can see that these lines here, these are real lines. Now, this will all help us understand how to draw the diagrams sooner or later. So, the principal focus of a convex lens, as we said, is where the rays hit the lens parallel to the axis or meet. So the principal focus of a concave lens, on the other hand, is where all of the rays hitting the lens parallel to the axis appear to come from. So this point here, this principal focus here, on a concave lens is where all of the rays that are hitting this hitting the lens in a parallel way, all of them appear to come from, whereas here is where all of the parallel light rays appear to meet. And actually, it's not even appear because they actually do meet, whereas this is they appear to come from. Now, there's another key thing that you need to know. So the whole meaning of the axis of the lens, which is this dotted line that we said passes through the center of the lens, is just this line that helps you understand whether they are diverging or converging. And then that allows you to find out what type of lens is it. Now, another thing, the principal focus on either side of the lens and the distance from the center of the lens to the principal focus is called the focal lens. So the focal lens of a convex lens, let's write that in green. So the focal length here is a distance from the center of the lens to the principal focus. And that's what we call the focal length. Now, of here, it's the same thing. So it's a distance from the center of the lens from the principal focus, and that's what we call the focal length. Now that's all of the key parts about ray diagrams, and we'll keep going about that in a second, but let's just talk about the 3 rules for refraction in a convex lens and the 3 rules for refraction in a concave lens. So the 3 rules of refraction for concave and convex. So let's begin with convex lenses. Okay, so we're talking about the 3 rules. The first rule is that an incident ray parallel to the axis will reflect through the lens and travel in line with the principal focus. So the incoming light ray that helps you see this, if it's parallel to the axis, then it will then refract through the lens and pass through the principal focus on the other side. So let's look at an example. So if we had an incident ray like this, for example, going into the lens, what this rule is saying is that if it's parallel to the axis, which is here, so as long as it's going straight, basically, right into the eye, as long as it's parallel to the axis, it will then refract through the lens and produce and pass through the principal focus. So let me make this diagram a little bit clearer. So what it's saying here is that all of the lenses, all of the light rays, as long as they're parallel, then eventually they will all meet at a certain point, and this point will be called the principal focus. And that's what we're saying here. All incident rays that are parallel to the axis will all meet at a point called the principal focus. Now, the next key point is that an incident ray that passes through the principal focus will refract through the lens and travel parallel to the axis. So this is almost the opposite of what we just said. So it's saying that if there was an incident ray that passed through the principal focus, as all of these have done, and it refracts through the lens, then it travels parallel. So both of these rules are the same thing. It just highlights that, firstly, if it's parallel to the axis, then it will all meet at a point. And this next one is saying is if it all meets at a point and you know it's refracted, then it must be parallel. The final rule for this one is that an incident ray passing through the center of the lens will just carry on in the same direction. So what that means is if we had a convex lens like this and we just had a normal ray passing straight directly through, then this actually would not change direction. There will be no change in direction. Now let's then look at the 3 rules for the concave. So the concave suggests that if there was an incident ray that was parallel to the axis, then and it would refract through the lens and travel in line with the principal focus, then that means that it is refracted. So what that means is, imagine we were to draw a concave lens, and if we had an incident ray that was parallel to the axis and then did pass through the point and did seem to connect to a point which we saw that, then we know that that is parallel to the axis. Now, on the other hand, you've got the same thing here. So if you've got an incident ray that passes through the point of the principal focus and is refracted, then you know that it is parallel to the axis. I hope that makes sense. It's really hard to describe these things, but if you do have questions, I can go through it again. And again, the same rule applies, that if there was an incident ray that passed through the center, then it would just keep going in the same direction. It wouldn't change direction. So let's look a little bit more about image and ray diagrams and things you're likely to get asked in the exam. So lenses can produce 2 types of images. Firstly, remember, lenses form these images by refracting them and by refracting light, so changing the direction of light. So lenses can form a virtual image and lenses can form a real image. So a virtual image can be created when the rays are diverging. So that means a different place. Now, that just means that we're talking about concave lenses here, because we learnt when we were looking at the diagrams earlier here, that when we're talking about a concave lens, these ones diverge because they split apart. Whereas if we're talking about a convex lens, these converge because they move towards the principal focus. So with a virtual image, this comes from concave, and it means that when you have these rays as they're hitting it, they will all actually scatter away and diverge away from the axis. And then instead, we'll get a virtual image. So if you were to connect these points, if you were to keep them going at first, and it seems as if the image is almost coming from this side, and it's virtual because it's not actually physically there. So an example of this is when you're looking in the mirror. When you're looking in the mirror, you're physically seeing a picture of yourself, but you know that's not yourself actually standing there. So when you're looking at a mirror, let's draw an example for you. When you're looking at a mirror, what you've got is you've got a virtual image that's being created. So all of the rays are diverging so that the light creates the object that appears to be coming from a completely different place. So when you're looking in the mirror, you see a virtual image of your face because the object, your face, appears to be behind the mirror. So what you're saying is when you're looking at a mirror, you've got that boundary. The real you is standing in the front. Imagine. However, you appear to be standing behind the mirror. And that's an example of a concave lens. Whereas if it was a convex lens, then in reality, you'd actually be standing right next to you. It's a bit difficult to explain, but hopefully you understand what that means. So when you're looking at yourself, you see an image behind you, but you know that's not real. So that's why we call that the virtual image. You can also get a virtual image when you're looking at an object through a magnifying lens. So imagine you had a magnifying lens and you're looking at something really, really small and it appears to be really, really big. What you're doing there is you're then producing a virtual image on your magnifying glass because genuinely it's not there. Remember, we've got this object that appears to be coming from a completely different place than where this came from, the actual object came from. So that's what a virtual image would look like. Let's look about a real image. So when we're talking about a real image, this tends to be associated with those convex lenses. And what happens is the light is coming from an object that comes together to form on a screen. Because remember what happens is we've got these light rays and they eventually just join up at the principal focus. And as they join up on this principal focus, the real image is created. It forms this image on screen. So you've got a real image. For example, when you're looking at something with your retina, the screen is almost the back of your eye, and that's how you're able to see things. So we use convex lenses when we're looking at our eyes. So you've got our eye, and then we've got this retina point, and what happens is as the light rays pass through the lens, they then get focused onto this retina. And that's an example of a convex lens. And the reason why it's a real image is because it produces this real image almost on the screen. Whereas when we're looking at a mirror, it just produces this image that's actually behind. So it seems like it's a virtual image. Now, that's just the explanation. Let's talk about ray diagrams now. Ray diagrams is almost inputting our knowledge that we've just learned into diagrams. Now, they don't actually tend to be worth a lot of marks considering how hard they are as concepts, and I think that's because a lot of people get them wrong. So if you do get them right, then you will be getting marks that often other students don't tend to get. ray diagrams. So a ray diagram can help you form an image through a convex lens. Let's first talk about a convex lens ray diagram. So you'll start off with a line. And on this line, you're going to have your lens. So remember, we talked about how convex lenses, even though they're shaped like this, in a diagrammatic form, so on a ray diagram, convex lenses are represented with a line with an arrow going up and an arrow going down. So let's draw the convex lens in the middle. So that acts as our convex lens. Then what we're going to do is we're going to put a point here, and a point here, and a point here, and a point here. Yes, this is live, by the way. So what this is you've got your different focal lenses. You've got F here, and you've got F2 here. So F1, and then F and F. And we'll talk about focal lenses in a minute. So we talked about how the focal length is the distance from the center of the lens to the principal focus. But we'll apply that knowledge right now. So you're going to then have an object. So when you have your lens, you're normally looking at an object. So let's say our object is 2 focal lenses away. Now our object could be, let's say, a flower. Now we'll be looking at this object through our lens here. So what we're going to do is you're going to pick a point on the top of the object and draw a ray going from the top of the object to going parallel to the axis. So the axis is this black thick line in the middle here. So what you want to do is draw a line from the top of the object going parallel, which is like this. Let me do it like that. And then what you're going to do is you're going to draw another ray from the top of the object to the middle of the lens, like this. Sorry, it's not supposed to be as wobbly as I just drew it. Okay, so you have 2 lines there. Now the incident ray that's parallel to the axis, so this first one that we drew at the top there, this is refracted through the principal focus on the other side of the lens. So this first line is then refracted through the principal focus. So let's say the principal focus is this point here. So this is the principal focus. So what happens is you then draw from that point going through to the principal focus. And then what you want to do is get your second line that you drew from the top of the object going through the middle of the lens, and you want to also connect that. Keep that going, so keep that line continuing in the same direction that it's going in. Like that. Now what happens is the line that goes through the principal focus and the line that you've just continued the line of meets at a certain point. And at that point, that is where the image has now been formed. Okay, so I hope that makes sense. So you see the image, you draw the top line going parallel to the axis. You then draw another line going from the top of the object to the center of the lens. You then, with the top line, draw it going refracting through this key principal focus here, and which you'll be told, so this will say principal focus. And then you'll draw another line which just continues on your second line, and they'll eventually meet at a point, and that is where the image forms. Now, you mark where the rays meet, and that is the top of the image. So key thing here is that is a top. The reason why it's the top of the image is because we've just shown you the top of the flower here. But if we were to do the same thing for the bottom of the flower, then it would produce an image somewhere up there, and then that would be the bottom of the image. So a key thing here is that you can see that the image is upside down. do ask me if you have any questions, because I know this is a difficult topic. Now you're going to repeat the process for a point on the bottom of the object, as we just said, and you're going to realise that the bottom is also on the axis. So repeat the process. When the bottom of the object is on the axis, the bottom of the image is also on the axis. So let's repeat the process for the bottom. So we've got the first line, which is supposed to be parallel to the axis, and then you've got another line which is supposed to be going through the centre, but ironically that is the same line as the line we've just drawn. So then what you're going to end up happening is the line will just keep going straight through the centre, because what do we say? If there was a line that's going straight through the middle of the lens, then it won't change direction. So this bottom of the image hasn't changed direction. So then you get the bottom of the image on the axis there. So then you basically have the image formed upside down. Okay, now there's some key things that you need to remember here. When you're talking about, if you're ever asked to describe an image, then you'll be asked about three key things. Firstly, the size of the image. Is the image produced bigger than the object, or is it smaller? Secondly, you need to talk about, is the image inverted? Like we said, is it upside down, or is it the right way up, so upright? And the third thing that you need to do when commenting on a ray diagram is looking at, is it a real image or is it virtual? And that's based on our understanding of whether it's convex or concave. Okay, so in this case, let's see. Okay, wait, before I go on to talk about whether they are these three things, you also need to look at something else. So focal lens lengths and how the distances from the lens can affect the image. So let me just explain what I mean when I'm talking about this. So imagine, let's draw these lines again, key lines here. So you've got the axis, because I'm going to draw three different diagrams for you. So three different diagrams here. And on these three diagrams, you're going to have your convex lenses on each of them. Now on the first diagram, we've got the focal lens 1 and the focal lens 2. So what this means is that it's just two focal lenses away. So in normal standard English, it's just double the distance the object is than if it was one focal lens away. So let's draw the object now. So let's say the object is the same thing, the flower. Now, because it's two focal lenses away, it's similar to the one we've just drawn. So you've got the top of the object touching the axis. Let me make this smaller so it can fit in 1 second. Because imagine that's the flower. So you've got the top of the flower, and that should make, firstly you want to do the parallel line to the axis, and then you want to make that go through the principal focus point. So imagine that's going through there. And then you've got your second line going from the top of the object through the center, and just keep that going. And then you've got the point where they intersect, and that is where you've got the top of the image. So that's just exactly what we've drawn. And that's what happens when an image is two focal lenses away from a convex lens. Now, if it was between two focal lenses and one focal lens away, then it produces something a little bit different. So let's go through that now. So imagine this is one focal lens, this is two focal lenses, and let's say that image of the flower is actually found somewhere between these two. No. We're still going to apply our knowledge in the same way. So what's going to happen is, because there's 1 to 2 focal lenses away, you've got the same thing. So the top of the image touches the is parallel to the axis, and then it goes through the principal focus point. And then you've got the top of the object going through the center, and then the point at which the image is made is here. Now, although it's not easily shown because these diagrams are not to scale, the difference between the two focal lenses and the one focal lens would be that with the two focal lenses, the image produced will be real, inverted, and the image produced should be the same size. So when something is two focal lenses away, that just means that the size of the image is going to be the exact same size of the real thing. But when we have something that's one focal lens away from us, that means, or between 1 to 2, sorry. So if something's between 1 to 2 focal lenses away from us, then logically that means it's closer than the thing that was 2 focal lenses away. And that means that we'll actually get an image that's bigger than the real thing. And this applies to logic. If you want to understand this better, think about it. So if you're looking at an object and you move closer to that object, you're reducing the focal lenses between your eye, the lens in your eye, and that object. And as you're reducing the distance, the things become clearer and bigger. For example, if you were to look at your hand and then move your hand closer to your face, somehow everything in your hand seems bigger. And that now makes sense. So apply that logic to this diagram here. Because it's between 1 to 2 focal lenses, it produces a bigger image. Now we need to talk about the other properties. So we've talked about the size, but remember we said that we also need to know, is the image inverted and is it real or virtual? Now, even though the size depends on the focal lenses, something that doesn't depend on the focal lenses is whether it's real or not. Because it's a convex lens, all of these images will be real. But if it was a concave, which we're going to look at after this, then that would be is this image inverted? And yes, it is inverted. Because as you can see, the top of the image here forms the bottom of the eye there, and then the bottom of this image, the bottom of that forms a top here. So it forms an upside down image. And therefore that's it. So real, inverted, and the size is dependent on how many focal lenses it is away. Okay, so now you may be asking, what about if it was nearer than one focal lens away, though? So we've talked about if it's two focal lenses, if it's between 2 to 1, or if it was one focal lens. Now, if it's one focal lens, then it actually produces something entirely different than what we've been learning. So if it's less than or equal to one focal lens, then what happens is, let's draw this flower. Because it is so close, what happens is you've got the line here that goes through the principal focus, and then you've got the line going straight through the center. And instead of the image being... Actually, sorry, let me do that again. So you've got the line through the principal focus, and then that one going there. And because the object is so close to you, these lines actually never cross. And when these lines never cross, what happens? You actually get a virtual image because they will then cross on the other side. So these two will then cross on this side eventually at this point here. And then you end up getting a virtual image of the flower on the opposite side to the one we've been learning. So you now have the virtual image here. So if it's between one focal lens and 0 focal lenses, you actually get a virtual image, and it's bigger than the real object, but it will be on the same size as the lens, and you can see that it's not inverted, it's the same way up as well, so it's upright. So those are the differences in the 3 different focal lenses. You don't need to know if it's further than 2 focal lenses. You just need to know that if it's at 2 focal lenses, that's exactly what happens. Really valid question there. Well done. Okay. So we've talked about convex lenses, now on to concave lenses. I hope what I'm saying makes sense to you. But let's talk about concave now. So concave lenses, we're going to talk about the ray diagrams. Okay, let me just move this away. So remember, concave, in terms of ray diagrams, they don't look like this. They look like you've almost got two V's, and you're connecting these two V's with a line like that. So let's begin, as usual, by drawing the axis out. It's a really thick axis. So drawing the axis out. Then what you're going to do is you're going to draw your lens. So we've got our concave lens. So it's going to look like that. And now you have your concave lens. So what you're going to do is you're going to draw your object. So whatever object you're looking at. So let's say again, let's bring back the flower. So let's just forget the focal lenses for a minute and just see how concave lenses form images. So again, it's a similar process. So you take the top of the image and you draw the line parallel to the axis, and you then take that image and go towards the center as well. So you've got two lines now, one towards the top and one going through the center. Now, what's actually going to happen is, remember, in concave lenses, instead of the lenses going like this and converging, they actually do the opposite and go the opposite way and diverge. And you may be thinking, okay, well, if they diverge, how will they ever meet? How will they ever form an image? So what you're going to do is you're then going to instead join up these lines. So you're going to draw those lines and then join up these lines here and join up that line here. So join up this one and that one. And then eventually it will actually meet up at a point on this side of the lens. So on the left-hand side of the lens. And what will then eventually happen is that you will get a virtual image. So let's talk about how this affects the different, how this is affected with the different focal lenses. Oh, and a key thing here actually is, so let me just read you this diagram to make sure that you're getting this perfectly right. So when you're drawing the ray diagrams of these concave lenses, what you want to make sure that you do is that, so you've got your object here. What you really need to make sure you do is you draw the line here and you draw the line going through the center. You draw them diverging. And then you want to make sure that when you're connecting them, you're drawing a dotted line, because these are virtual lines, remember. These don't actually exist. And then they will meet at a certain point, and that will then be called the principal focus, where the top of the image will be. So remember to draw the dotted line for that part of it. Now, as we said, because these are dotted lines, the concave lenses produce a virtual image, and it always produces a virtual image, whereas convex lenses can produce real images unless it's less than one focal length away. And again, here you can see that the image will also be the right way up, because this will be the top. This here will be the top of the flower, and then that will be the bottom. So not only is this image virtual, always, but the image will always be upright, so the right side up. And another thing is that the image will also be smaller than the object. So no matter how many focal lenses it is away, the image produced will always be smaller than the object and found on the same side of the lens as the object. So luckily for you, you don't have to remember if it's one focal lens, it's this much, it's two focal lenses. No matter what, for concave lenses, you will always have an image that's virtual, that's the right way up, that's smaller than the object, and that's found on the same side as the object. Okay, so those are the key things about ray diagrams. I hope you understood that. And I think it's all about getting familiar with the topic. So maybe after this stream, just try and blurt out, if you can remember, what are the different rules and how it works. But now let's talk about magnifying glasses. Okay, so when we're looking at magnifying glasses, these work to create a magnified virtual image. If you were here earlier on, used to make a virtual image, because when you use a magnifying glass, you're looking at a small object and you're getting it in a much bigger version. So you're basically getting a virtual image. So the whole purpose of a magnifying glass is to get this virtual image, and that's magnified. So firstly, we've got some requirements then. We need the image to be virtual. We need the image to be bigger. But that's already confusing some of the ideas we learned, because we already learnt that with concave lenses, so let's see how we combat this. So this then means, and then the object must be magnified closer to the lens at one focal length. So the object must be magnified, no, the object being magnified, must be closer to the lens than the focal length. Now, since the image produced is a virtual image, the light rays don't actually come from the places where the image appears to be. So you can't actually project a virtual image onto a screen. You can use a magnification formula to work this out. But if we were to draw the diagram for this, you would get your axis, as usual. You would get your convex lens, and we'll be using a convex lens for magnifying glasses, because if we want to make a bigger one, then we can't use concave. And in order for it to be virtual, we know that convex lenses only produce virtual images if it's less than one focal length away. So that's where magnifying glasses only work if you're holding your magnifying glass really close to an object, less than one focal length. If it was greater than one focal length, then you wouldn't get a virtual bigger image that's correct. So you've got your convex lens here. Let's say the object was, and let's say the flower was right here. So then with this flower, we're going to draw the two key lines, so from the top of the object to the center of the lens, and then from the top of the object, touching the center point of the lens, which is there. But these points won't actually meet, because remember, this is the virtual image that's less than one focal length. So you then draw the dotted lines. So normally this convex lens would meet at a certain point, and then we would then draw the dotted lines from those points. And you will then get that much bigger picture going on over there. So that much bigger image. And what the purpose of it meeting at this point here is because you have your eye here, because you're looking at it. So that's where that will meet, in the retina. Okay. So you've got less than one focal lens. The top of the flower touches the middle of the lens, and then in the parallel way, and then the top of the flower touches the middle of the lens in the center, and then they then meet at a certain point. That's where the eye is, but then they will then zoom out and you'll see the larger flower there. So that this is the virtual bigger image that you wanted. So if you were ever asked, how does a magnifying glass work? If you don't understand how the system works, then just memorize how the diagram would look. So remember, you have that one convex lens, you have your axis. Oh, remember, convex lenses will be represented by using the arrow actually. So you have your one convex lens, you have your axis, you have your small object, less than one focal length. Draw that, that will touch there. Draw that, that will go through somewhere, and then they'll then connect and draw that big flower, that enlarged version of what you want to see. Okay, so that's all about lenses done. So we're almost done with this topic. We just have to go through visible light, infrared, black body radiation, sound waves, ultrasound, and how we explore Earth. So, visible light. So when we're looking at visible light is made up of a range of different colours. Electromagnetic waves, as we said, cover a massive spectrum. And the reason why they cover a massive spectrum is because they're just released when particles and atoms, they're releasing this radiation. And as they release this radiation, there's so many different varieties. So we can only see a part of this visible light spectrum. So this is a range of wavelengths that we perceive as different colours. So each colour has its own narrow frequencies. So when we're talking about the different colours of the visible light, each colour has its different frequency. And it's actually a range of frequencies, not just specifically one. For example, violets range from 400 nanometers and reds go to 700 nanometers. So we have the colors of the rainbow: red, orange, yellow, green, blue, indigo, violet. So violet's wavelength is 400 nanometers, but red's wavelength is 700 nanometers. So you can tell a similar thing happens to really quickly like that. Probably more gradual than that. This is for triple science. But yeah, I don't know if this part is for combined as well. This whole live stream is supposed to be for triple though. Okay. Now, colours can also mix together to make loads of other different colours. So the only colours you can't actually make by mixing together are the primary colours. So that's why they're called primary colours. So if you've ever wondered what differentiates the primary colours, well, you might know already that the primary colours are used to make all other colours. But another key thing is that you cannot make colours, they already exist. And the primary colours are red, green, and blue. So, red, green, and blue. Now, different colours absorb, transmit, and reflect different wavelengths of light, because we looked at how waves absorb, transmit, and reflect light, and different colours have different abilities. The reason why they have different abilities is because you can see here that the wavelength is different. It means that it can do different things. So when you have an opaque object, which is an object that does not transmit light, so opaque object does not transmit light. So when you have an opaque object, when you hit a visible light wave at an opaque object, they actually absorb some of the wavelength of the light and they actually end up reflecting others, but they do not transmit light. Now, what do we mean by transmit? Transmit means that a material like glass, for instance, you have your incident ray, and then say if it moves, and then it comes back. So hitting, you've got your normal at this point, and you've got your incident ray, hits at this axis, say if it moves closer, and then it moves further away again. So that's a translucent object. A translucent object is basically see-through, so it can transmit it, but opaques cannot transmit it. So what do they do instead? They either absorb or they reflect, or they can do both. Now, the color of an opaque object depends on which wavelength of light is most strongly reflected. So it might be hard to understand this, but when you're looking at an object, understand the color of the object is that light that's being reflected onto that object. For example, if you were to be looking at a red apple, okay, and if you were looking at this red apple, and obviously the apple is majorly red here, so what you're seeing here is that you're seeing visible light that okay, so you've got your visible light, which is a mixture of all of the different lights, and what happens is with this red apple, the color red appears so strongly because the wavelengths corresponding to the red part are most strongly reflected. So the visible light hits it, and the wavelengths that are reflected are the red wavelengths, and then the wavelengths that are absorbed are all of the other colors. Okay. Same thing as, say, if you had a banana, and this banana was obviously yellow. So if you had visible light that hitted this banana, what would happen is the colors that would most strongly be reflected out would be the color yellow, and the colors that would be absorbed would be all of the other colors in visible light. Okay. Now, for opaque don't transmit any light, and for opaque objects that aren't a primary color, there may be reflecting either the wavelengths of light corresponding to that color or the wavelength of the primary colors that could mix them together. So just as we said, we looked at a banana here, and we know that the color yellow isn't actually a primary color. So it doesn't just, when I say it transmits the yellow, that means that it transmits the color combination of primary colors that creates that yellow color. So in this case, the banana would be reflecting both red and green light, not necessarily yellow, and that makes our eyes detect the banana as yellow. Now, that makes us think about objects that are white and objects that are black. So if we had a white object, and if we had a black object, what would happen? So white objects, imagine the visible light is this blue arrow here, white actually reflects all of the visible light that it absorbs, because white is more of just the absence of light. So it reflects all of the wavelengths of light equally. It has equal wavelength of light being reflected, whereas black equally absorbs all of the wavelengths. So that's why they say that if you wear black, you're going to be hotter, because it's absorbing all of the radiation, so you're more likely to be hotter. Whereas because white reflects all of the radiation, you're less likely to be hot because it's reflecting all of the colors in radiation. So our eyes see black, the color black, as the lack of visible light and the lack of color. Now, transparent and translucent. So, transparent is see through, and translucent is partially see through. These can transmit light, which means that not all of the light passes through. Now, some wavelengths of light may be absorbed or reflected by transparent and translucent objects. So, transparent or translucent object's color is related to the wavelength of light that's transmitted by it. So now let's look at color filters and how color filters work. So when we have a color filter, what you're doing is you're filtering out all of the different wavelengths of light. So say if you had a purple color filter, or a violet, every other color except the colors that are used to make that violet, except that primary color. And then what this does is it only reflects the violet colors and certain wavelengths, and the rest are absorbed. So in this case, when we're talking about filters, these are actually translucent partially. So that means that um, it actually allows the transmission. So it transmits the color violet, and it actually absorbs all of the other colors. And as it transmits the color violet, that means everything you see will then have a violet frame on it. So, transmit that color. If this filter was red, then it will only transmit red. And then the rest will be absorbed. And say if we were to use a blue filter now. So blue filter is a primary color, so that means that blue will be transmitted. And then say if you were to look at an actually blue box, for example, what would happen is the blue box would appear as blue as it was beforehand. Blue light would just be reflected from the object's surface and is transmitted by the filter. Now, if the object was red, however, or any color that could not be made from blue light, the object would appear black. So if you had a blue filter on and you were wearing the color red, what would happen is because red cannot be made by the blue, because remember, red is a primary color, so it cannot be made by blue, what happens is the red actually appears black in the filter. Because what happens is none of into the red, nothing can be absorbed, nothing can be reflected, so nothing can be reflected, but everything is just absorbed into it and it becomes black. So you can try it now. If you have a method of using a filter, say you were to put a primary color filter of blue or just a blue post-it note against a light, then anything that could not be made by the color blue, for example red or green, what you would do to those is that would then turn it black. Now filters that aren't for primary colors and let through both the wavelengths of light can then be added to make that color. So it depends on the filter's capabilities, but you should generally just grasp the essence of that. Okay, so every single object absorbs and emits infrared radiation. We've talked about visible light, let's move on to infrared. I hope you guys are going well. Well done for watching it all the way up till here. And I hope your exams are going good. You're almost done, you're almost there. Okay, so with infrared radiation, this directly has an effect on the temperature. And we'll talk about exactly how that does that in a second. So, all objects are constantly, continually emitting and absorbing infrared radiation. Right now, you're sitting there or standing up, emitting and absorbing infrared radiation. Now, infrared radiation is always emitted from the surface of a material. So it's impossible to say, for example, if you had a box here, and if you had the center inner part of the box, infrared isn't being emitted from there. Infrared is only emitted from the surface of the material. Now, the hotter an object is, the more infrared it emits. So if this cube was hotter, then this means that the amount of infrared it emits would be more and more and more. And an object that is cooler would have less emitting of infrared radiation. Now, objects at a constant temperature will emit infrared at the same rate that they're absorbing it. So let's just go through that again. If you have a constant temperature, for example, right now, say if you're not increasing or decreasing, you're at the same temperature, then what that means is that you're emitting infrared at the same rate at which you're absorbing. Because remember, no matter what, you will always be emitting and absorbing infrared. So even when you are constant temperature, you'll still be emitting and absorbing it, but at the same value, at the same rate. Now, some surfaces and some colors absorb and emit radiation much better than others. For example, if you had a matte black surface, it's much better at absorbing a white one. And that brings you to the required practical, which is all about the Leslie's cube. So, the Leslie's cube is just this hollow, watertight cube that on each of the surfaces it has different materials. So, the Leslie cube. Now, it's hollow, it's watertight, and it's a metal cube made out of aluminium. And what you're going to do is you have these four vertices. So, not four vertices, sorry, four vertical faces. So, you have face 1, face 2, you have face 3 on that side, and face 4 on this side. Now, on the top, it's not actually a face, so you can just discard the top. And what happens is on each of the four faces, you have different surfaces. For example, on face 1, you could have a matte black surface. On surface 2, you could have a paint. And you can then have shiny metal as one of the other ones. Because remember, this is aluminium. And then you can have a dull metal. Now what's happening here is you've got this cube and you're going to use it to investigate the infrared emissions of different surfaces. So you're going to place this Leslie's cube on a heat-proof mat. Okay, so you've got your Leslie's cube on a heat-proof mat, and then what you're going to do is you're going to boil water in a kettle and you're going to fill the Leslie's cube with the boiling water. So you'll normally have a bit of a groove here, which will allow you to fill, using your kettle, I don't know what that drawing is, to fill the water in. So you're going to fill boiling water into the cube. Now what you're then going to do is whilst you're waiting for warm up, you're going to hold a thermometer against each of the four faces. So it depends if you want to use individually 4 different thermometers or 1 thermometer per face. We're going to use these thermometers, and the point of it is to measure the temperature and record the temperature of the 4 vertices. Now, whilst you're waiting for it to warm up, you should find that all of the faces are initially the same temperature. So first, they should be the same temperature. Then what happens is you're going to hold the infrared detector at a set distance. So your infrared detector just looks like another little cube and just has this circular part on the outside. So this is the infrared detector, the same thing that's used in infrared cameras. So you've got your infrared detector, and it's just going to record the amount of infrared it detects. So you're going to measure the temperature, and you're going to measure the infrared reading from the infrared detector. And then what you're going to do is you're going to repeat the measurements of each of the cube's vertical faces, making sure the position of the detector is at the same distance each time. Because what you want to do is the infrared will only be able to measure 2's radiation. So you have to repeat it 4 times to be able to get each of the 4 different values. And you should find that the more you detect more infrared from the black surfaces than the white ones, and you detect more from the matte, is the black. It absorbs more of the heat and absorbs more of the infrared. Now, as always, do this experiment more than once and make sure that it's repeatable. So don't try to touch the boiling cube because it could burn your hands. Make sure that if you're carrying a full kettle, make sure that people are away from the side so it doesn't injure anybody. And that's the Leslie's cube required practical. Now, sometimes they actually alter the practical by saying instead of having to hold the thermometers up against each one, it might be a little bit inaccurate because some of it could be going into the surroundings. So instead, apply a little bit of wax, and then you're also going to put a nail. And you're going to time, so you're going to apply the same amount of wax on each of the 4 surfaces, and then what you're going to do is you're going to time how long it takes for the wax to melt completely and the nail to fall on the surface. And that's another method of doing this. Now, that brings us on to black body radiation. So, a perfect black body is an object that absorbs all of the radiation that hits it. So, nothing is reflected, nothing is transmitted, it's just perfectly absorbing everything. So, imagine we have this perfect black cube here, and it's absorbing every single bit of radiation that you give it. Perfect black body. Now, all objects emit electromagnetic radiation due to the energy in their thermal energy stored. So, as we said, everything emits electromagnetic. It doesn't even have to be necessarily hot. It will always emit some radiation. Now, the radiation isn't just in the infrared part of the spectrum, it covers a range of wavelengths and frequencies. So, we're not always just emitting infrared, we're emitting loads of different types of electromagnetic radiation. And perfect black bodies are the best absorber and emitter of any type of radiation. Okay. Now, the intensity and the distribution of the wavelengths emitted by an object depend on the object's temperature. So we said intensity. Intensity just means the power per unit area. So when we're looking at the key word intensity here, we're basically describing how much energy is transferred to a certain area in a certain amount of time. So the energy transferred in a certain area over a certain amount of time. For example, in 3 seconds, 2,000 joules of energy was transferred to 2 meters squared worth of area, for example. So that's the intensity. So the power per unit area, so how much energy is transferred over time in a certain area. Now, we also need to look at the distribution of wavelengths, and the distribution is affected by the temperature. So, as the temperature of an object increases, the intensity of every emitted wavelength also increases. So what we're saying here is that when the temperature of something increases, say if the temperature of this perfect black body increases, what happens is that's emitting the radiation, they get much more intense. And as they get much more intense, this means that okay, so they're emitting shorter wavelengths. Now, so as the temperature of an object increases, the intensity of every emitted electromagnetic wavelength increases, and therefore you get shorter wavelengths than longer wavelengths. And this causes the peak wavelength, which is the wavelength with the highest intensity, to decrease. So let's look at a graph. This might make it a little bit easier. So we're looking at a graph, and you've got the intensity, so how much energy is transferred in a certain area over a certain amount of time, and then you've got the wavelength here, how long the waves are. So initially, as the wavelength increases, the intensity increases, because as we said, the intensity is increased by the temperature, and every emitted wavelength increases. However, as the intensity starts to increase really rapidly, what happens is you start to get wavelengths that are much shorter in length. Oh, sorry. Much shorter in length, like that. So initially, as the intensity increases, the wavelength increases, but beyond a certain point, the intensity starts increasing really rapidly, and this causes the wavelengths to start becoming shorter and shorter. And this means a peak wavelength decreases. You don't need to know too much about this, so don't be too confused. Okay, let's move on to radiation. So when we're looking at radiation, this is the thing that affects the Earth's temperature. So the overall temperature of the Earth depends on the amount of radiation that it A, reflects, that it B, absorbs, and that it C, emits. So the radiation is dependent on those three things: the amount that it absorbs, the amount that it reflects, and the amount that it emits. And that's what all of these three factors affect the temperature of the Earth. Now, during the day, there's lots of radiation. You've got the sun, which is transferring the visible light, and the infrared as well. And this is then absorbed, and this causes an increase in the local temperature. However, at night, there's less radiation being absorbed than is being emitted. So this causes a decrease in the local temperature. So overall, the Earth's temperature stays fairly constant, and you can see how that works here. So let's look at this diagram. So imagine you have the Earth's surface here, and you've got the different layers. So first you've got the layers where you have the clouds, and then you've got the layers of the atmosphere, and then you've got space on the outer layers. So what happens is during the day we get lots of radiation come in. So some of the radiation is reflected via the atmosphere. Some of the radiation is reflected from the clouds. Some of the radiation is reflected from the surface of the Earth. But again, we don't just have reflections, we also have the amount that's being absorbed. Some is absorbed into the atmosphere and then absorbed into the surface of the Earth. Now, we also know that radiation is emitted into space. That doesn't have to necessarily come from the sun. So some radiation is just emitted from the atmosphere, radiation is emitted from the surface, radiation is emitted from the clouds. Now, changes to the atmosphere can cause changes to the Earth's overall temperature. So if the atmosphere had started to randomly just absorb lots of radiation, but not emit the same amount of radiation it's absorbing, then what happens is there'll be an overall rise in temperature, and until emissions start equaling again. So it's just saying if the atmosphere was to increase and absorb more radiation and stop emitting the same amount, the temperature will actually start rising because we're absorbing too much infrared. And that's what we're going through right now with the global warming. Okay, so now we've gone to sound waves, then ultrasound, and then we'll be looking at S waves, P waves, and then we'll be done with the live stream. Well done for you guys being all the way here. So, sound waves. So when looking at sound waves are caused by vibrating objects. Mainly particles, but sound can also be caused by other things as well. So vibrating objects, and what happens is these vibrations are passed through the surrounding medium as a series of compressions and rarefactions. So there's some difficult terminology there for you. So these vibrations of these objects pass through the surroundings as compressions and rarefactors. So remember, sound is a type of longitudinal wave, which means that it travels parallel to the direction of the energy transfer. Now, sound waves generally travel faster in solids than in liquids, faster in liquids than in gases. So what we're saying here is that sound, so when we have our three states of matter, solid, liquid, and gases, they actually travel the fastest in solids and the slowest in these gases. Now, the reason why is because we know that sound waves need vibrating objects, and in solids, because the density is much higher, there's more particles there, so the more vibrations could occur, and therefore the compressions and rarefactions would be much more bigger. So what we're talking about when we're saying compressions and rarefactions is normally when you're seeing a diagram of sound, it looks like this. Just random lines, and some areas are much more denser, some areas are really bare, and overall there will be like a pattern. For example, so the areas of compression are the areas where there's lots of lines, and the particles are pretty much compressed. And areas of rarefactions then are the opposite. So they are where, there's just gaps between the particles. So say if you had a loudspeaker. Now, a loudspeaker is ejecting out sound. So what this then does is the sound waves that the loudspeaker is generating travels through the air as a series of compressions and rarefactions. So you've got compressions, rarefactions, compressions, rarefactions. So this diaphragm in the speaker is vibrating back and forth, and as this part of the speaker is vibrating back and forth, it then causes the air particles to vibrate back and forth, and these compressions and rarefactions are made. Now, the reason why it travels best in a solid object is because imagine you've got the structure of the solid here. So as the sound moves and the vibrations happen, the vibrations will be felt a lot quicker, because if this starts to vibrate, then these three neighboring particles will start to vibrate, and it will be passed on really quickly. Whereas with the liquid, if we had a vibrating particle, the next particle could just be a bit further away. So it would have to actually go and move towards it in order to pass on the energy. Now, that's why sound cannot travel in space, because in space it's a vacuum. There are none of these particles that we're talking about in solids, liquids, and gases in the air, because there's no particles to move to or vibrate to. So sometimes the sound waves will eventually just travel into someone's ear and reach the eardrum, where they might hear the sound. So just how we can hear sound is another key idea. So imagine you have your ear, and this is your outer ear. Don't worry, this isn't biology, so you don't need to know too much about this. And then you've got this whole process here. So you've got your outer ear, and what happens is the vibrations move towards your eardrum, going in that direction. And then what happens, you actually have your eardrum here, and then it hits the eardrum. It then causes a oscillation, and you see that there's different parts of the ear. The main part, let's call that the semicircular canals. So you've got the movement of sound going from the outer ear to the eardrum to the semicircular canals, and then this then sends messages to the auditory nerve to the brain. So then it sends messages and links to the auditory nerve in the brain. And that's how we hear. So you've got the sound, it's funneled into from the surroundings via our outer ear, hits a eardrum, goes through the semicircular canals to the auditory nerve to the brain. So these vibrations that initially hit the eardrum are called end up hitting these really small bones, and so this is just the middle bit between um, the eardrum and the semicircular canals, and these bones are called the ossils. And it's ironic because they're the ossils because they're passing on the oscillations, the vibrations. These ossils then go through the semicircular canals and then to the cochlea. So this bulging part is called the cochlea. And in the cochlea, what happens is it turns these vibrations into the electrical signals, which then send it to the brain. So going through this process again, you've got the outer ear, sends it funneled into the eardrum goes to the ossils go to the semicircular canals, the semicircular canals go to the cochlea, where it then converts it into electrical signals for the auditory nerve in the brain. Now, different materials can convert different frequencies of sound waves into vibrations. So humans can hear the sound wave range between 20 hertz and 2000 hertz. So that's a massive range. Now, microphones can pick, I'm sorry, not 2000, 20,000 actually. Now, microphones can pick up sound waves outside of our human range, but if you tried to listen to the sound waves that these microphones would pick up, then you would just not hear anything because it's outside your range. So if you were to ever go on those videos where it had the sound waves of between 1 and 100,000 hertz, you will only start hearing it naturally from 20 to 20,000 unless your hearing is bad. So our human hearing is limited by the size of and shape of our eardrum, as well as the structure of the parts of the ear that can vibrate to transfer the energy. Now, sound waves, just like all waves, can reflect and refract. So sound waves will be reflected by hard surfaces. For example, if you ever talk about echoes, that's a reflection of sound waves, and that's why you tend to see it in caves, because caves are made of really hard, flat surfaces. So as you reflect your sound, it's then reflected. Now, sound waves can also refract, and sound waves can be refracted media. For example, if you were to start speaking and then go in the water and start speaking, you notice that the sound in the water is really muffled. And the reason why is because the densities are then changing. So if you're entering a denser material, it actually speeds up because when a wave travels into a different medium, its wavelength changes, but its frequency remains the same. So its speed might also change. So what we're saying here is that sound waves can actually refract because of if it's going into denser materials or if it's going to less dense materials. And then what happens is as they enter a denser material, then it will speed up. Now this is because when a wave travels into a different medium, its wavelength changes, but its frequency remains the same. Okay, so that is it for those sound waves. Now let's talk about ultrasound. So with ultrasound waves, this is have these. This is it's the same thing as a sound wave, but the frequency is much here. These can easily be converted into mechanical vibrations in order to produce sound waves beyond the range of human hearing, so above 20,000 and below 20 hertz. So ultrasound is above human hearing. Now, ultrasound waves are a type of wave that gets partially reflected at two boundaries. So you may know that ultrasound is used to look at babies and infants in pregnant women. So when we're looking at them, they're partially reflected at boundaries. And what then happens is because they're reflected, they're at the boundary of two different mediums, so for example, from a solid to a liquid, then what happens is some of the waves end up being reflected at that boundary between the two mediums. So this is called partial reflection. For example, the baby and it's detecting the mother's blood. What happens is it can easily be go through the blood, but then perhaps at the head, because of the skeletal system, it will actually partially reflect. And some will keep going as well, but some will partially reflect, and this can help produce images, just how X-rays reflect when it gets to bones and denser material. Now, the time it takes for the reflections to reach a detector can be used to measure how far the boundary is. For example, obviously, say if it was to reflect at the boundary of the eye as well, what would happen is you can tell that it takes longer to reflect at the boundary of the eye because it has to travel a further distance. So then the computer puts together this image based on how long it takes. Now, ultrasound is really useful in a lot of different ways. So as we said, medical imaging used in the body, the boundary of the two different media, the exact timing and distribution of these echoes are processed by a computer, and no one actually knows for sure if ultrasound is safe, but it's definitely more safe than X-rays. And ultrasound is also used for finding flaws in material. So things like pipes and metal, ultrasound can be used by entering that material and reflect in that material any flaws. So say if there was a crack in the material. Echo sounding is a method in which you use high frequency sound waves, ultrasound, for boats, and it finds out the depth of the water. So you can actually find out how deep the water is. If you're in a boat and you're submerged under the water, you can find out how deep the water is just by emitting sound waves and looking at this process of echo sounding, seeing how long they are till they are reflected to locate things deep in the water. Now, the final thing is how we can use S waves and P waves to look at the structure of the Earth. So waves have different properties. As we said, wave speed is different, and this depends on the material they're traveling through. So when a wave arrives at a boundary between materials, a number of things happen. It could be partially reflected, meaning it could be absorbed, or some could be transmitted. Now, the wave may continue traveling in the same direction, but at a different speed, so it can be transmitted, for example. Now, the wave, as we said, so studying the processes and properties of parts of the waves can actually help us understand the structure of the Earth. So, if you've ever wondered how we get the structure of the Earth, do we just think that the Earth is made of these circular structures that then have the outer core, then have the inner core? So, the inner core is supposed to be solid. The outer core is supposed to be liquid. And the mantle is supposed to be a mixture, so it's supposed to be almost solid, but it's kind of moving solid. Now, looking at the way waves move has helped us create this structure. So you've got two types of waves: S waves and P waves. So S waves are transverse waves. Now, things light, this can travel through the liquids and through S waves can travel through liquids. So that's why when you look at the distribution of S waves, they're only going through the mantle and they don't touch the inner core or the outer core. But if we were to look at P waves are longitudinal. So when they sent P waves through, they actually went through mainly the center. So they were mainly limited by the center. And they only went out a little bit to the liquid, but they mainly focused on the center, which told them that the center must be solid for the longitudinal to travel across it. Because remember, they are felt most in the solid materials. So these are felt most in the solid materials, and that's why it's shaped the Earth's structure. And finally, earthquakes and explosions, these can all create seismic waves. So when there's an earthquake, it produces seismic waves, which again are these vibrations, and we can detect them using seismometers. Seismologists work out the time it takes for the shock waves to reach each seismometer. And then when the seismic waves reach a boundary between different layers of material, then some waves will be absorbed and some will be refracted. But most of the time, if the waves are refracted, they change speed and result in a curved path. So if you've ever wondered how do seismic waves just eventually just randomly stop, well, it's because they move through the different boundaries and then gradually as they're refracted, they just change their speed and become slower and slower. Okay, so well done for being here. We've now finished our waves topic. So overall, in terms of the live streams I've created, I've gone through the two biggest topics, forces and waves, in these live streams. This live stream has a whole head forces, so all you have is magnetism and space physics. I might do one just for your exam. I'll see if I have time, but I'm going to do a geography one. So well done for joining. Appreciate you guys so much, and thank you for watching. I will be doing a geography later on if you do geography. So see you then, or if not, good luck for your physics for tomorrow.